Okay, in this video we're going to take a look at potential in a uniform electric field. We're going to take a look at a general case of finding the electric field from potential, and then we're going to take a quick look at equipotential surfaces. Now, we set up uniform electric fields whenever we have two parallel plates. And what we're going to do is use the potential difference formula for the general case that we learned last time. So we're basically just going to, start with some simple stuff to make sure that the ideas behind how to use each component of that equation is intended to be used and what the meaning behind it is. So we're going to start by writing delta V is equal to minus the integral from a to b of e dot ds. Okay, so in this particular example, we're going to be going from a to b towards the right. So d is towards the right. Our path, for now at least, will be straight across, which is going to be towards the right. Alright, so in setting up this integral, the first thing we need to do is figure out what we're going to do with the dot in this dot product. And in this case, the path, it's going to be, because it's to the right, each little path element ds. Now, ds is just, one differential piece of the path. If it were a winding path and it were moving towards the right, and it looked like this, when you're at this location right here, then tangent to that point would be your ds. And right here, tangent to that point would be your ds. And of course we have another one right here that's perfectly horizontal, and so that would be your ds. So whenever you're moving from A to B, you've got an infinite number of these little path elements that are going straight across. So each one of those is a ds. Now, what you're doing with E dot ds is you're comparing the direction of the electric field with the path itself. And because E is everywhere parallel, you can get rid of the dot for the dot product. So we get delta V is equal to the negative of the integral from A to B of E ds. Now, E is a constant, and when we integrate with respect to the path, nothing's going to happen, so we can pull that out. We get delta V is equal to minus E times the integral from A to B of ds. And when you go from A to B and you're integrating ds, all we're looking for is the length of the path, which was parallel to E, which in this case, because E was in the same direction as ds, the path length is just going to be equal to d. We went from A to B, which is the distance d that we've defined here. So we end up with delta V is equal to minus E times d. Now, this is how you find the potential difference as you move through that space between parallel plates. So let's put this into a little perspective for you. Just give you a small example here. Let's just say that the electric field for these parallel plates is equal to 10 newtons per centimeter, and D is equal to 50 centimeters. Well, if I want to calculate as I go from one plate to the other, if I go all the way from here to here, right, and I want to calculate what was the change in the potential, then it would just be delta V is equal to 10 newtons per centimeter times 50 centimeters. Actually, that's a fairly large plate. Let's go with 5 centimeters. All right, so 5 centimeters. And so delta V would turn out to be 50 volts, right? I hope you didn't say right, because I purposely made a mistake right here. That's all supposed to be negative, right? because we have a negative in our formula. And that should make sense because we go from a high potential to a low potential. Charges are always, positive charges are always going to move from high to low. And we're always going to assume that it's a very small positive test charge if we just generically talk about things moving around. If it's a negative charge, it will be explicitly mentioned that it's a negative charge. So we should have a negative 50 volts on this answer because we went from high potential to low potential, so we lost voltage. Or to put it in specifically energy terms, we lost energy. We lost electric potential energy and turned it into kinetic energy if this was a particle which was free to move from one plate to the other. Now, don't forget that the work done in a uniform electric field is going to be equal to QED. And that basically comes from, if we move the negative side to the other side of the equation, so it becomes a minus delta V, then delta V, so we get minus delta V is equal to ED. So we're just going to prove this real quick. And then delta V is equal to delta U over Q. That would be equal to ED. And then we know that the relationship between work and change in potential energy is that they're opposites of each other. And since this is a negative change in potential energy, it's a positive value for work. So we get work over charge is equal to E times D. So work is equal to QED. And I always liked this equation because it was easy for me to remember. The local public broadcast station is WQED, so I always like that one. Now the next thing I'm going to do with this equation is I'm going to solve it for E. And the reason for that is we end up with another relationship which may not be obvious at the outset. So in solving this for E, we end up with minus delta V over D. And this is sometimes called the potential gradient. And if the potential gradient is a known function, then that means you can determine the potential or the electric field. You know, you can actually work back and forth with that. And this is going to be a big deal for us in this course, of course, because we use calculus. So let's look at the general case. All right, so we started with delta V is equal to minus the integral from A to B of E dot ds. And this equation is in the integral form. All right, it's in the integral form, and you can often take an equation which is in an integral form and you can write it in a derivative form. Maxwell's four equations come in both varieties. You can either look at it in terms of derivatives or you can look at them in terms of integrals. So we have delta V is equal to minus the integral of V dot ds, and in order to convert this, I'm just going to undo all the integration stuff and leave it in terms of differentials. So delta V becomes dV, and we just lose literally that integral sign so that we get minus E dot ds. So now I'm going to solve this for E, and we get minus dV ds. Okay, now this is basically one-dimensional for us, but if you go into all three dimensions, we can write E is equal to minus del times V. And del is an operator which basically is going to take our derivative in three dimensions. It's beyond the scope of AP Physics C, so we're not going to be using it, at least not in the videos. We might do it in class as an extra activity, but anyways, you just take your delta symbol and you flip it upside down, and that becomes the del operator. And the del operator is going to give us the derivative of the function in x and y and z. But the point is, the electric field is the negative gradient of the potential. It's the negative gradient of the potential. Now, when it comes to understanding the what we're doing here, that making this relationship between the electric field and electric potential, it's helpful to imagine this like we have a topographic map. And if the electric potential is changing in the negative direction, that basically means you're going like downhill. There is an almost perfect analogy between gravitational fields and energy and electric potential fields and energy. And so to show this relationship, it's very helpful to look at this in terms of a topographic map. And let's just take the case where we have a positive charge. And I place the positive charge right here. In terms of a topographic map, the positive charge would be analogous to having a mountain or a hill. And this is going to be sea level right here. I'm going to make this sea level. And basically you start out at sea level when you're infinitely far away and there's zero potential at this point. Whether it's gravitational potential or it's electric potential, it doesn't even matter. There's just zero potential when you're infinitely far away. It's the same thing with gravitational fields as it is electric fields. And so as you get closer to the electric charge, it starts to rise sharply. Let's see if we can get a better curve on that. Okay, so it starts to rise sharply like that. And now it's like you're climbing a mountain. And of course, there's going to be an asymptote right here because you can't ever actually get to on top of the charge at 0, where x would be, or r would be equal to 0. So, you're going to climb this mountain higher and higher and higher. And you have a potential at this location, and this location, and that location, and that location. And the space between each one of these lines may represent 1 volt or 10 volts, or if it's in terms of topographic map, it might be 1,000 feet or 100 feet or 10 feet. You can have multiple scales here. The idea is just to see that as you get closer, the potential increases. So let's just say this is 10 volts, and this one is 20 volts, this one is 30 volts, this one is 40 volts. All right, so as you get closer, the potential is increasing. So as you go up the hill, delta V is positive, and as you go down the hill, delta V is negative. But the electric field points in the opposite direction. Okay, so if we look at this from like a helicopter view, so here's our positive charge here, we know that the electric field lines point radially outward, and that these potential lines here that I'm showing now coming out of the page towards you would be those potential lines coming out of the page towards you. And so as you go in this direction right here, as you're getting closer and closer to that charge, delta V is increasing, right? But the electric field is in the opposite direction. And that's why we have that negative sign, that E is equal to minus dV ds. Because as I go in that opposite direction, the field is actually getting stronger. So that's the positive charge. The negative charge, of course, is exactly opposite. Instead of looking at it as though you're going from sea level up a mountain, you're going sea level down into a valley. And it becomes increasingly more negative as you go down into the valley. Okay, so let's look at one more thing. Should be review of last year, but let's take a look at the case where we have two parallel plates once again, positive plate over here, negative plate over here, and the electric field points from left to right. And we've got these locations, three locations, A, B, and C. And we can go from A to B, we can go from A to C, and then we can go from B to C. And what we're going to look at here is just investigate the dot product a little bit more. And what is our change in potential going to look like? Now, as we go from A to C, or A to B, we have a path, we'll just say our path element ds is going to be pointing straight down our page here from A to B. That is perpendicular to the electric field, and therefore the change in potential for going from A to B is going to be equal to 0. If we look at it as we go from A to C, we're going to be moving in this direction. So here's our path element ds, and this is the direction of E, and so the angle of phi is going to be this. Remember that angle phi is always the angle between two vectors when placed tail to tail, and that the magnitude of the dot product is determined by using the cosine of phi. And so ultimately what becomes important isn't the overall length of the path, it's just going to be the part of the path which is parallel to the electric field. And so for this, we just get delta V is equal to E times D. And we got, for going from A to B, let's rewrite that very quickly, just so it's clear where that came from. This was delta V is equal to E times 0 because the path element ds was 0. There was nothing that was parallel to the electric field. And then finally, as we go from B to C, we don't have to use the dot at all because everything is entirely parallel. Okay, so now we're going to take a quick look at equipotential surfaces. And an equipotential surface is a surface in which all points are at the same electric potential. And so if we're looking at it in terms of gravitational potential near the surface of the Earth here, then the equipotential surface would be a flat plane, basically, because we're so close to the Earth, we don't see the curvature, and so it becomes a flat plane. So your desktop would be a equipotential surface for gravity. Well, because gravity is a uniform field down here at this level, we consider it to be a uniform field, then the equipotential surface for a uniform electric field is also going to be a plane. And we see that whenever we have parallel plates. Now, it doesn't have to be a flat plane. An equipotential surface can really take on any shape. And if you take a look at a charged particle, it has that spherical Gaussian symmetry. And so, if you wanted to look at the equipotential surfaces around a charged particle, then you would be looking at a sphere. Some of the important features for an equipotential surface is that no work is done moving the charges around on the equipotential surface. Now think about that. In order for work to be done, there has to be a force which is parallel to D. So if you have an equipotential surface here, we know that the electric field is going to be pointing up or down relative to that surface. So the potential, let's just say the potential here is at 10 volts. And you want to take a charged particle and move it in this direction, parallel to the surface, like rolling a marble on a desktop. Once it's in motion, it takes nothing to make it move. All right, so if we're not looking at that teeny tiny change in kinetic energy associated with getting it started, then there's no work which is done, okay, because we're looking for the work which is done by the electric field in this case. So as you move across an equipotential surface, no work can be done. However, if you go through the surface, then work can be done, because maybe we went from 10 volts so that now V is equal to 5 volts. Our potential is now 5 volts. So as I went from 10 volts down here to 5 volts, I know that there was a loss in potential, which tells me there was an increase in the kinetic energy. I lost potential energy, but it increased into kinetic energy if this was a particle which was free to move. And in order for that energy to be transferred to the particle, work must have been done, because that's our definition of work. Okay, so is done whenever you're moving parallel to an equipotential surface, and work is only done as you go from one surface to another. Okay, now if this happens to be parallel plates here, then that would mean that I might have many layers in here. And the point is that you can look at this really kind of like a book. A book is composed of chapters, and if you want to change the potential or change the energy, you have to go from one page to the next. You don't go across the page. When drawing equipotential surfaces, there's a relationship between the potential and the electric field. And we said that basically they're going to be perpendicular to each other. That's what we saw on a previous slide. Okay, so you need to be okay with drawing out what an equipotential surface looks like. And so let's do an example with parallel plates. This is the easy one to understand. And we'll say that this plate is at 20 volts and this one is at 0 volts. Now, it doesn't matter whether it was 120 and 10 or 100, it can be whatever. And positive plate, negative plate, and we know that the electric field points straight across from one plate to the next. All right, now the equipotential surface is everywhere that the potential is the same. And we know that the potential is going to be the same everywhere along a line which is parallel to the plate and perpendicular to the field lines. And so we're going to have an equipotential surface here, like this. And you can break this up into as many divisions as you want depending on your purpose. All right, so what I'm doing here is I'm saying this is 20 volts. I'm going to make my next equipotential surface 15 volts. This would be 10 volts, and this one would be 5 volts. You could have gone in the negative direction. If you went from negative, if this was considered to be minus 20, then we lost an additional 20 volts, and this would become minus 25, minus 30, minus 35. But the way this is set up, that's not the case. But the point is that equipotential lines are going to be drawn perpendicular to E. And so if you draw yourself a positive, or just a dipole, so we've got a positive charge here and a negative charge here, the electric field looks something like this. And you are tasked with drawing the equipotential lines. And there's no set number here of these field lines I'm putting in. I'm just giving myself enough that I can get a good gauge on what the shape of my equipotential should be. Now we know that everywhere along these lines that we should be perpendicular. So if I put an equipotential here, remember I'm just trying to get perpendicular to my field lines, which have to be drawn reasonably accurately. Then I get this. So here's, that's not exactly perpendicular, but there's that. And we know that there's going to be an equipotential that does this right down the middle, and that these are going to get squished together in here, and they kind of bubble out like that. This is really harder to do than I thought it would be using a tablet. But okay, so it's going to be almost circular down here in the middle. Let me just make these not dotted lines, but solid. Typically they're dotted, but I'm having a hard time doing dotted lines. Okay, and it kind of, these field lines get weaker out here, and so it takes more space in order to cover the same potential. So in other words, the gradient is less when you get further away from the charge, on the outsides of these dipoles. And so they get squeezed together here in the middle, and they spread out towards the back. Okay, but we're always attempting to keep our equipotential line perpendicular to the field lines. And that's how you would draw these. Now, how many of these are you going to have to draw? Maybe one, for the test. I don't even know if it would be on the AP exam. The important thing is that you understand what you're looking at. If you ever look at a diagram of electric field lines and they start asking you questions about potential, that's the important thing. So interpretation, yes. Drawing, maybe.